In the previous two lectures, we've learned that acids produce hydrogen ion in aqueous solution, while bases produce hydroxide ion in aqueous solution. You probably already know that acids and bases, quote, neutralize each other. Now, what exactly does this phrase neutralize really mean? Well, it simply means that if you add a base to an acid, it will tend to destroy the properties of the acid and vice versa. The reason for this, I think, is pretty easy to see. Hydrogen ions, H positive, and hydroxide ions, OH minus, cannot exist in the same solution at any appreciable concentrations because they have a strong tendency to combine to form water molecules. In fact, the equilibrium constant for this reaction would just be equal to the reciprocal for the equation for the dissociation of water. In other words, if the equation for water ionizing to form hydrogen ions and hydroxide ions has an equilibrium constant of 10 to the minus 14th, then the reverse reaction, where hydrogen ions and hydroxide ions combine to form water, would just have an equilibrium constant that would be the reciprocal of Kw, or 10 to the positive 14th. This is such a large equilibrium constant that for all practical purposes, the reaction between a strong acid and a strong base essentially goes to completion. And this fact allows us to utilize a laboratory procedure called a titration to experimentally determine the concentration of some unknown solution of an acid or base. If you are enrolled in a high school chemistry class at the current time, there's a good probability that you will be called upon to perform one or more acid-base titration labs before the year is over. There are two key requirements to performing a successful acid-base titration. First, you must have some good experimental procedure that allows you to add the acid or base in a carefully controlled manner and to measure how much you've added with good accuracy. Secondly, you must have some way of telling when you have added just enough base to just neutralize the acid or vice versa. Okay, let's define a couple of terms. As we have seen, hydrogen ion and hydroxide ion react in a 1-to-1 mole ratio. So if we had 1 mole of acid to start out with, we would need 1 mole of base to just neutralize it. The point where you have added just the right amount of base to neutralize the acid or vice versa is called the equivalence point. But how will you know when you've reached this point? Let's assume for the moment that we're going to be titrating an acid by adding a base. Well, one way would be to use an instrument called a pH meter to measure the pH of the solution as you slowly add the base to the acid. At first, the pH of the solution will be quite a bit below 7, since acidic solutions have low pH values. But as you add the base, you would expect the pH of the solution to rise because you're neutralizing the acid. So the solution would become less acidic as base is added. When you have added just enough base, the equivalence point, the acid should have been just neutralized. There would be no excess acid or base left over. The hydroxide ions that were added from the base would have neutralized, quote, all of the hydrogen ions from the acid, leaving nothing remaining. Well, not exactly nothing. The hydrogen ions and hydroxide ions would have combined to form water. But you would still have the slight ionization of water existing in equilibrium with a small concentration of hydrogen ions and hydroxide ions. We, of course, have discussed this equilibrium in detail. It's just the self-ionization of water. So at the equivalence point of this point, the solution should have a pH of 7. It would be neither acidic nor basic. So you could watch the change in the pH on the pH meter and stop titrating when the pH of the solution reached a value of 7. It's a good plan and it would work, but it's not too convenient. And this would require that you have access to a pH meter. There is an easier way. You just use something called an acid-base indicator. A slightly inaccurate definition, but I think a good one to start out with, is that an acid-base indicator is a substance that is one color in an acidic solution and another color in a basic solution. There are a lot of acid-base indicators in nature. Red cabbage is an acid-base indicator, so is tea. As a young child, I remember squeezing some lemon juice into a large glass of iced tea. The color of the tea immediately became much lighter, and I wondered how such a small amount of lemon juice could change the color of the tea so dramatically. It was only many years later that I actually learned what was happening. One of the most popular indicators in a high school chemistry lab is something called litmus. Litmus happens to be red in an acidic solution and blue in a basic solution. Students often use something called litmus paper, which is nothing more than paper that has been soaked in litmus, to test whether solutions in fact are acidic or basic. If the paper turns red, or something that looks kind of red, maybe more pink than red actually, we know that the solution we were testing was acidic. If the paper turns blue, or something approaching that, we say that the solution was basic. I brought into the studio today some litmus paper. What I always have found terribly interesting about this is called red litmus paper, and this is called blue litmus paper. I have no clue why they have called this red and blue for centuries. They look pretty much the same to me, but anyway, and neither one looks red or blue. Here I have a piece of what is called red litmus paper. I'm going to put this into a solution of a base, and according to what we've said, it should turn blue or something approaching that. I would say that pretty much approaches blue. Now, rather than use blue litmus paper, if what we said is true, if I haven't been lying, then if I dip this into an acidic solution, it should turn back to, well, red or pink. Let's see if that's true. The second beaker, in fact, contains a solution of hydrochloric acid. And I think that certainly shows that litmus paper does do what they claim it's supposed to do. Another indicator commonly used in high school is phenolphthalein. It happens to be colorless in an acidic solution and red in a basic solution. It actually is red, but it often appears more pink than red because we typically only use a few drops of the stuff in a relatively large volume of solution. While we aren't going to take all the time that would be required to actually perform a carefully and correctly run titration live, I would like to at least walk through how one is typically performed in high school. To do a titration, you use a specialized piece of equipment called a burette. As you can see, a burette is a long graduated tube that you fill with the solutions that you are titrating. They have a stopcock at the bottom that allows you to add acid or base in carefully controlled amounts. Burettes are calibrated with the 0 mark at the top so you can easily measure how much solution you've drained out. Let's suppose you had a solution of some acid like HCl, and you were supposed to determine its concentration by titrating it with a solution of some base like sodium hydroxide. What you would do would be to carefully fill a clean burette with the acid solution you were planning on titrating. Before you actually fill it, you usually have to first add some acid solution to the burette, roll it around the sides of the burette, drain it out, and discard it. You do that because after you clean the burette, it is still wet. And if you were to just add the acid solution, the water in the burette would dilute the acid, reducing its concentration. You would end up determining the concentration of the diluted acid in your burette rather than the undiluted acid whose concentration you were actually supposed to determine. After filling your burette with acid, you would actually drain out a bit of the acid into a waste container because you have to make sure that the tip of the burette is filled as well. Otherwise, the first little bit of acid that you, quote, drain out never actually makes it into the reaction flask. You would read the initial volume. You could actually start at the 0 mark, but that's inconvenient. So you just start at whatever the initial volume reading happens to be. I'm going to pretend that our initial volume reading on the acid is 0.60 milliliters. You then drain some acid out of the burette into the reaction flask and take the final burette reading. We'll pretend that our final acid burette reading was 22.75 milliliters. You are often instructed at this point to add several milliliters of distilled water to the reaction flask, but are told that you don't have to measure how much you add. This step often confuses students. Why measure the acid so carefully if you're just going to toss in some unmeasured amount of water? I mean, it seems like you've messed up the entire lab. Of course, you haven't, and I'll explain why a bit later. You then add a drop or two of some indicator, typically phenolphthalein. Contrary to popular belief, if a little indicator is good, a lot isn't better. A couple of drops will do just fine. Now you take the initial reading on the burette that holds your basic solution. Let's say that initial reading is 1.40 milliliters. The solution of base that you're using has to be what is called a standard solution. This term is a bit misleading because every other time we've used the term standard, it meant some specified value, like standard temperature was 0 degrees Celsius and standard pressure was 1 atmosphere. The term standard here in no way implies some specific concentration. It just means that we know the concentration of this solution with a high degree of accuracy. As a student, you will almost always be provided with this solution, and its concentration usually has been experimentally determined by your teacher. This was always the great test for my lab assistants, whether or not I trusted them enough to actually have them standardize the solutions that we were going to use in our titration labs. It was a big responsibility, because if the standardized solution was wrong, everybody's lab results were wrong. We'll assume that the concentration of our standardized solution of base is 0.276 molar. Now you just add base slowly and carefully to the solution of acid, swirling it to keep it mixed. At first, it's a rather boring procedure. I'm sorry, very exciting, of course. Everything in chemistry is always exciting, right? Anyway, you keep adding base carefully. After a while, you will see a pink color appear. That's the phenolphthalein changing from its colorless color. Does a colorless color make any sense? Well, you know what I mean. To a pink color. But when you swirl the solution, it will turn colorless again. The initial pink color occurred simply because the solution hadn't been thoroughly mixed. So there were local spots where the acid had been completely neutralized and the indicator changed color there. But when everything was swirled and mixed, the solution was still acidic, so the pink color disappeared. But eventually you will reach a point where adding just one more drop of base will cause the solution to turn pink, and the pink color will remain even after you swirl the flask. Let me show you what this actually looks like. Before today's lecture, I titrated a solution of hydrochloric acid with a solution of sodium hydroxide until I was right at the equivalence point. I'd like you to see just how sensitive this system is to the addition of just 1 or 2 drops of acid or base. We're going to add 1 drop of base to the solution that I had titrated. This is actually the base that we used earlier in this lecture. When I swirl this, this should turn pink, and indeed it does. Now, if what we said is true, then adding 1 drop of acid should cause that solution to clear up. Well, let's see if it in fact will. Wow, that's pretty dramatic. I must have seen this 1,000 times, and I still love to look at that. You have now reached what is actually called the end point of the titration. It's called the end point simply because it's the point where you end the titration, since the color of the indicator has changed. It also should be the equivalence point, which is the point where the amount of base you've added is just equal to the amount of acid you started with. The end point of a titration and the equivalence point theoretically should be exactly the same, although they can and sometimes will differ by an insignificant amount. It's just that you have no way of visually observing the equivalence point. So some books and teachers don't like to call the point where the indicator changes color the equivalence point, but prefer to call it the end point. I agree with that and do personally make the distinction, but really it's nothing worth making a big deal out of. So we can call the point where the indicator changes color either the end point or the equivalence point if you wish. Once you reach the end point of the titration, you take the final reading from the base burette. Let's say that reading is 18.65 milliliters. So now let's take a look at the data we've taken down from this laboratory procedure. The final reading on our acid burette was 22.75 milliliters. The initial reading was 0.60 milliliters. The difference between these two readings tells me how much acid was added to the reaction flask. That comes out to be 22.75 minus 0.60, or 22.15 milliliters. The final reading on our base burette was 18.65 milliliters. The initial reading was 1.40 milliliters. This means that it took 18.65 minus 1.40, or 17.25 milliliters of base to neutralize 22.15 milliliters of our unknown acid. And the concentration of that base that was added was 0.276 molar. We can now calculate the concentration of our unknown acid. But before we do, let me ask you a question. Should the concentration of our acid solution be greater or smaller than 0.276 molar, the concentration of the standardized base that we used in the titration? Stop the video and think about that if necessary. Hopefully you realize that the concentration of the unknown acid has to be less than 0.276 molar. Here's why. It only took 17.25 milliliters of the base to neutralize 22.15 milliliters of the acid. But since the acid and base reacted in a 1-to-1 mole ratio, the number of moles of acid and base had to be the same. So 22.15 milliliters of acid contained the same number of moles of acid as there were moles of base in only 17.25 milliliters of base. If the same number of moles of acid are in a larger volume than the base, the acid must not be as concentrated as the base. Okay, let's do the actual calculation. If you feel confident, try this yourself before viewing the solution. The key to this entire calculation is to realize that at the equivalence point of the titration, the number of moles of acid had to equal the number of moles of base. We can calculate the number of moles of base that we added from the volume of the base that we added and its concentration. The molarity of the standard base was 0.276 molar, and we added 17.25 milliliters of this base, which is 0.01725 liters. So the number of moles of base added is equal to 0.276 moles per liter times 0.01725 liters, which comes to 0.004761 moles of base. At the equivalence point, the number of moles of acid has to equal the number of moles of base. So the number of moles of acid we had in our reaction must also be equal to 0.004761 moles. And since this acid had been contained in 22.15 milliliters of the original acid solution, the concentration of this unknown acid solution has to be equal to 0.004761 moles divided by 0.02215 liters, which means the molarity of our unknown acid was about 0.215 molar. Now I'd like to make a few comments. First, why didn't it make any difference that after we added the carefully measured 22.15 milliliters of our unknown acid to the reaction flask, we then added an unmeasured amount of distilled water to the flask? Think about this, and again, pause the video if necessary. The idea here is that once you've added the carefully measured acid to the reaction flask, you can add as much water as you like. It doesn't change the number of moles of acid in the flask. It will change the concentration of the acid in the reaction flask. I mean, the more water you add, the more dilute the solution in the reaction flask. But, so what? You aren't going to use the total volume of solution in the reaction flask in any calculation. When you titrate the acid with the base, it takes the same amount of base to neutralize the acid whether you add water or not. The amount of base required depends solely on the number of moles of acid you originally added. And adding water to the reaction flask doesn't do anything to the number of moles of acid that have to be neutralized. Okay, let's try a problem on our own. We're getting near the end of this series of lectures, so I'm going to jazz up the problem quite a bit. This is intentionally going to be probably the longest problem in terms of the amount that you'll have to read that you have probably ever seen. Our real goal here is not really about the mathematical calculations. It's about breaking down a very wordy problem, thinking about it, drawing pictures as necessary, and visualizing what really is going on before we start tossing around numbers. Here's the problem. A student performs a titration to determine the concentration of an unknown acid solution. She titrates the acid with a standard solution of base whose concentration is 0.553 molar. The initial reading of her base burette is 2.85 milliliters. The initial reading on her acid burette is 1.35 milliliters. She adds some of the unknown acid to a reaction flask that she has washed and rinsed with distilled water but hasn't dried. The final reading on her acid burette is 34.75 milliliters. She adds a couple drops of phenolphthalein to the reaction flask and then adds 44.50 milliliters of distilled water to the flask. She then adds base from her base burette. The final reading on her base burette is 28.65 milliliters, but she realizes that she has overshot the endpoint of the titration because the solution is almost dark red instead of pink. So she then adds more acid to the flask from her acid burette. When the solution just turns and stays light pink, her acid burette reads 35.15 milliliters. What was the concentration of her unknown acid solution? Now, contrary to what you may be thinking, I didn't present this problem to frustrate or aggravate you. I presented it more for two basic reasons. First, unless you understand what you're doing, it is highly unlikely that you are going to solve this problem correctly by using some sort of formula or factor label or proportions or whatever. Secondly, it is highly probable that you will not completely understand what is going on here on the first reading. Remember how we emphasized that you may need to read a problem several times, draw pictures, etc. I'm really not as interested in whether you got the correct numerical answer to this problem as I am in how you thought about it. So here we go. Let's break this monster down into more manageable pieces. Let's go through the problem sentence by sentence and see what it is telling us and what we should be thinking. First sentence. A student performs a titration to determine the concentration of an unknown acid solution. Okay, nothing unusual there, but it tells me exactly what I am trying to calculate, the concentration of the unknown acid. I have to keep that in mind as I go through the problem. As I've said before, if you don't know what it is you are trying to find, it is highly unlikely that you will find it. Second sentence. She titrates the acid with a standard solution of base whose concentration is 0.553 molar. Straightforward statement. I know the concentration of the standardized base solution, which I know I will need to calculate the number of moles of base that are added to the acid. Nothing unusual here. Third sentence. The initial reading of her base burette is 2.85 milliliters. Again, nothing unusual. I need this number when I calculate how much base was needed to perform the titration and reach the equivalence point. Fourth sentence. The initial reading on her acid burette is 1.35 milliliters. Nothing unusual here either. I need this when I try to find out how much acid solution was added to the reaction flask. Fifth sentence. She adds some of the unknown acid to a reaction flask that she has washed and rinsed with distilled water but hasn't dried. Does it make any difference that she hasn't dried the flask? Or is this just a little trick designed to throw me off? Let me think. To calculate the concentration of the acid, all I really need to know is how many moles of acid were added to the reaction vessel, which I determine by how many moles of base it takes to neutralize it. Any extra water that's in the flask doesn't matter. It doesn't take any base to neutralize water, so it shouldn't make any difference if the flask was wet. I can ignore the statement. It was just a trick designed to throw me off. Sixth sentence. The final reading on her acid burette is 34.75 milliliters. Nothing unusual here. I need the final acid burette reading to calculate the number of milliliters of acid that were added. Seventh sentence. She adds a couple of drops of phenolphthalein to the reaction flask and then adds 44.50 milliliters of distilled water to the flask. Now I got to think. Adding a couple drops of phenolphthalein is fine. That's what she's supposed to do. But why is the volume of distilled water given? Makes me think I have to do something with this number. But what would I do with it? You usually add some distilled water to the reaction flask. But we've learned that how much you add doesn't matter and doesn't have to be measured. I'm bothered by the fact that the volume is given as 44.50 milliliters, but don't see why I would need that for anything. Looks as if this student didn't realize that she didn't need to know how much distilled water was added. I don't think this number can be used for anything, so I'm going to ignore it. Eighth sentence. She then adds base from her base burette. Okay, that's what she's supposed to do. Ninth sentence. The final reading on her base burette is 28.65 milliliters, but she realizes that she has overshot the endpoint of the titration because the solution is almost dark red instead of pink. So she then adds more acid to the flask from her acid burette. Now this is weird. What happened? Evidently she added too much base, probably didn't control her burette very well. It appears that she has over-titrated the acid and went right past the equivalence point. This appears to be a busted titration, but wait. She then adds more acid to the flask. Can she do that? Or has she messed up the whole experiment? Well, why not? She could have added more acid to the reaction flask the first time she added acid. Why can't she add just a little more now? It appears that she has figured out that if she overshoots the endpoint of the titration, she can actually just add a little more acid rather than having to start all over. 10th sentence. When the solution just turns and stays light pink, her acid burette reads 35.15 milliliters. So she has evidently now reached the equivalence point for the titration. Normally we get to this point by adding base until we get the light pink color. But since she overshot the endpoint, she has actually arrived at the correct endpoint by adding a little more acid. Is this okay? Why not? There's nothing that says you have to arrive at the equivalence point by adding any particular substance. The equivalence point is the equivalence point. It doesn't really matter how you get there. So now we know that we are at the equivalence point, and the real question is, how much acid and base did it take to get there? Well, I know how much base it took. The initial reading on the base burette was 2.85 milliliters, and the final reading was 28.65 milliliters, so she added 28.65 minus 2.85, or 25.80 milliliters of base to do the titration. But how much acid did she neutralize? We have two final burette readings, 34.75 milliliters and 35.15 milliliters. Which one should we use? It would have to be the last one. The first final burette reading didn't really turn out to be final because she overshot the endpoint and had to add more acid. She could have added this to begin with. The initial final burette reading can be ignored. It really wasn't final. Her acid burette started out at 1.35 milliliters and ended up at 35.15 milliliters. She added a total of 35.15 minus 1.35, or 33.80 milliliters of acid. So 25.80 milliliters of base neutralized 33.80 milliliters of acid. Now I am ready to do these simple titration calculations. The number of moles of base needed to react with the acid is equal to the concentration of the base times the volume that we used. This would be 0.553 moles per liter times a volume of 0.02580 liters, or 0.0143 moles of base. The number of moles of acid we titrated is equal to the number of moles of base it took to neutralize it. So there are also 0.0143 moles of acid. This many moles of acid were contained in a total volume of acid of 33.80 milliliters, or 0.03380 liters. So the concentration of our unknown acid is 0.0143 moles divided by 0.03380 liters, or 0.423 molar. Now, this is clearly a somewhat unusual problem, but I hope it illustrates why students who have approached chemistry by trying to memorize some formula or method run a high risk of eventually hitting a wall that they can no longer have the ability to climb over. There just isn't any real good substitute for understanding what you are doing. In the next lecture, we're going to learn how these acid-base indicators work and talk a bit about titrating weak acids instead of strong acids.